Welcome to massive open online course on basic principles and calculations in chemical engineering. Here we will discuss about the balances on transient processes as a module 9. Now under this module 9, in this lecture we will try to discuss about the material balance of transient processes. In the previous lecture we have discussed about the energy balance with heat of combustion reaction, analysis with examples, but those balances are steady state process. But here I will try to do some material balance where the process will be unsteady state, and also will describe with examples here. Now, what is that unsteady state process? The term unsteady state process basically refers to the process in which quantities or you can say that dependent variables or operating variables as a dependent variables within the system changes with time, and the unsteady state process is sometimes called as transient process. So, transient means here unsteady state process, you have to refer it like this. Now, let us consider this chemical engineering process where you will see that the process will be based on time consumption. Like in this case here one steel at a that certain condition and inside this steel some amount of liquid mixture. Let this liquid mixture is that propane and butane mixture, and in this mixture certain amount of propane will be there and certain amount of butane will be there with a mole fractions of like xp and xb. Here xp means mole fractions of propane and xb means mole fraction of butane. You will see that if we heat this steel of this mixture of propane and butane, you will see that the higher boiling point liquid will be remaining in the steel, whereas lower boiling point liquid will be vaporized, and it will be coming out from the top portion of this steel, and after that if we condensed it through a condenser, and it will be taken out as a liquid butane, because here butane will be coming out as it has the boiling point is less than that is propane, and the boiling point of butane is minus 1 degree Celsius, whereas propane boiling point is minus 42 degree Celsius. So, here in this case you will see that this vapor will be coming out, butane vapor will be coming out here or higher boiling point instead of that propane and butane mixture, any mixture of this different boiling point component if it is there. So, higher boiling point that liquid will be coming out as a vapor whenever it will be heated, and then it will be condensed out, and then it will be taken out as a that xd that is a distillate product after separation. Now, in this case you will see that in this steel whatever butane composition will be there inside this steel, during that heating process you will see that this composition of this butane will be changing. Now, that change will be with respect to time. If you boil for for a certain time, you will see that accordingly that composition of that butane in the distillate product will be there. Now, in this case that means here with respect to time this composition in the steel will be changing. So, this type of process is called that unsteady state process. Now, how long it will take to that condensed or you can say that separate this butane vapor from its initial concentration to a certain final concentration. So that can be obtained by this energy material balance equation, but that material balance equation will be as per unsteady state condition. So let us look back into the general material balance equation. We have discussed it in module 3 in lecture 3.1, where lecture serial number it is 7. So there we have discussed that this general material balance equation as accumulation within a defined system, that will be equals to input through system boundary minus output through system boundary plus generation within the system minus consumption within the system. That means in short we can write here accumulation will be equal to input minus output plus generation minus consumption. Now positive contribution to this system will be input and generation, and negative contribution to the system is output and consumption. So here it is seen in the figure that if this is the process unit, you will see that in this process unit input will be coming and whereas output will be like this in this stream, and you will see that this input and output, this will be that stream. So input stream and output stream, there will be certain amount of that components will be there at a certain flow rate. And during this process, in this process unit, if is there any generation there, like in a reaction certain at a certain condition, there will be some product that will be produced with the reactants. So there will be certain generation of the components. So that components will be also will be coming out as a output there. And then during that reactant you will see that during that reaction some reactants will be consumed, and it will be that will be that consumed. So that amount to be considered as a consumption terms. So in any process there this accumulation, input, output, generation and consumption terms will be considered for the overall material balance there. Now in this case if I consider that unsteady state material balance, in unsteady state processes the accumulation term in the mass balance equation cannot be neglected and must be accounted for. So if suppose there is a steady state process, that means there is no accumulation, in that case input and output plus generation minus consumption will be there. Whereas in case of unsteady state process, there you will see that input rate and output rate will not be same. So in that case some amount of materials will be deposited or accumulated in the system with respect to time. So that will be called as accumulation. So in that case accumulation you cannot neglect there. Here suppose in this flow process some amount of that materials will be coming in as that mass flow rate of m dot 1, similarly another component m dot 2 and another component m dot 3, those are coming into this flow process unit and they are coming out here as m 4 dot and m 4 dot 5 and that m 6 dot there as a mass flow rate there. Now in this case you will see that overall if this output total output is greater than this that input, then what will happen, you will see that there will be that amount in the system will be decreasing. Whereas if output is less than this input, you will see there will be an accumulation, that means here in the system the mass will be increasing with respect to time. So in this way this will be considered as unsteady state process where accumulation terms to be considered. Now let us write this unsteady state material balance in symbol. Here if we consider that the accumulation of mass in the system will be there with respect to time. So what will be the change of that accumulated amount with respect to time, that can be represented by this dm by dt, and where you will see that m dot in, that will be your mass of material that is coming into the system as a flow rate, here m dot in, and similarly m dot out, that is rate of mass of that material which is coming out from the system at a rate, that will be regarded as m dot out. Similarly, at the same time, if is there any material is generated in the system, then you have to consider that will be as m dot generation, whereas if is there any mass is consumed during that processes, that also you have to consider here as a rate of m dot consumption here. Now, this here m dot in, there may be more than one inlet. So, total inlet mass flow rate will be considered as summation of that mass of several inputs that you have to consider as a sum, whereas at output also you have to consider what will be the total amount of out based on the summation of all the output mass flow rate. So, in this way you can calculate. If there are suppose more than one components also, so separately for that individual components also you have to consider, and adding up all those components mass flow rate, you will get that the total amount of mass that is in will be coming into the system as an input. And if you are considering the flow rate of that individual components which will be coming out from the outlet, that also to be considered as a total mass out for that summation of all components, that will be regarded as summation of mi out, and it will be total output rate of that mass there. So, similarly generation and consumption to be considered. Now, this is regarded only for that multiple inlet and outlets condition. So, here m is the mass accumulated in the system, and m dot in is the inlet mass flow rate, that is mass per unit time. Even m dot out is outlet mass flow rate, that is mass per time. M dot generation, it will be generated mass flow rate, that is mass per time. Similarly, m dot consumption, it will be equal to consumed mass flow rate, that is mass per time. Now, you can express in terms of moles also, not only that only mass, it will be considered as a mole also as a rate. So, that will be mole per time there. Now, let us do an example for this unsteady state process here. Let us consider the small steel is used to separate propane and butane mixture at 135 degrees Celsius, and initially contains 10 kg moles of mixture in that steel, whose composition is that x is equal to 0.3 mole fraction of butane, and additional mixture here xf that is mole fraction of butane as 30% is fed at the rate of 5 kg mole per hour. Now, if the total volume of the liquid in the steel is remain constant during that operation, and the concentration of the vapor from the steel which is coming out as a xd is related to that concentration of the butane in that particular steel, will be expressed as xd will be equal to xs by 1 plus xs. So, based on this composition of distillate product, you can calculate how long will it take for the value of that concentration of that butane in the steel to change from its concentration from 30% to the 40%, that you have to find out. So, this okay, let us solve this problem here. So, as per this problem, we can have this steel here, and in this case feed here composition is 0.30 as xf, and composition of propane and butane mixture here it is given as propane it is 70% and butane as 30%, and initially the steel is filled of 10 kg mole of propane butane mixture, and after that that feed will be supplied as a 5 more kg moles per hour rate to this steel, and then heating it, and during this heating you will see that butane vapor will be coming out from that steel, and accordingly you will see that there will be that concentration of that butane inside the steel will be changing with respect to time. Now that that distillate whatever will be there inside that still, that will be coming out as a vapor, and it will be after that condensed, it will be taken as some D amount, and where this butane concentration in that distillate amount would be xd. Now this xd change, that is xd with respect to time, that will be change, and accordingly you can say that this xd basically how it will be related to that concentration of the butane in that still. So it will be related by this equation here, xd will be equal to xs by 1 plus xs. What is xs here? Xs is nothing but that concentration of that butane in the still. You are at a time t. So in that case, how to solve this problem to find out that if suppose butane concentration is changing from 30% to 40%, how long it will take to have such change of this mole fraction from 30 to 40%. Now in this case we will do that material balance first, unsteady state material balance. Like we know that material balance as accumulation that will be equal to inlet minus outlet plus generation minus consumption. This is your material balance equation. Now in this case, since there is no reaction is going on and there is no generation of the components, so we can neglect it as 0, and also there is no consumption of this any materials for reaction. So in that case we will also neglect that consumption terms, so we can neglect it. So finally we can have this material balance equation as accumulation will be equal to in minus out. Now what is the accumulation there? Now if we consider only that butane material, so if we do that material balance for this butane, so we can write here initially butane concentration was there will be some amount that is there 30% and 70%, all the time it will be that they are in this still 30%, but with respect to time you will see that it will be changing, because there will be that amount of butane will be changing and it will be vaporized and it will be coming out from that still. Now the total volume of that still inside that that is still will be remain constant. So that is I think 10 kilomole, sorry 10 I think it is given as per problem, it is 10 kg mole of mixture will be kept constant there inside that still. So accordingly we can say that accumulation will be what? Now during that vaporization process, the concentration of that still, that is in butane concentration, will be changing. Now what is that change? That we do not know. Let us have this change is delta x here s. S is the here still concentration, here butane concentration, that still. Now the change with respect to time maybe that with respect to time delta t, that change of that concentration will be delta xs. Now since the volume of this still is remain constant, it is 10, so we can multiply this with 10, then it will be your that total amount of butane at a particular time, and there will be a change of butane with respect to delta t time, it will be 10 into delta xs. So this is your accumulation. And then what will be the inlet of this butane in this still? Now there is a flow rate of that as per problem, this flow rate is given, the feed flow rate is given 5 kg mole per hour. Now in this 5 kg mole per hour flow rate, what would be the amount of that is excess there, or you can say that except that is butane vapor in that feed. So we can write here then since it is 5 kg mole per hour flow rate and concentration is xf there. So we can write 5 into xf, and since we are considering within a period of time, that is delta t, so we have to multiply it like this. So it will be coming out at this this amount of material is in the steel, and then out will be equal to then again out at the flow rate of 5 of that mixture, so that total volume of that steel will remain constant 10. So 5 into here outlet concentration is basically xd here, and the time is delta t. So in this way you can write that out let material for this short period of time t, and generation is 0, and consumption is here 0. So finally this equation you can get. Now dividing by t and taking the limit at approaches to 0, so we can write here d into xss dxss by dt, that will be equal to 0.15 minus 0.5 into xd. Why 0.15 here? Here xf is basically here 30%, that is 0.30. So 5 into 0.30, it will be coming as here I think it is 5 into 0. This is 1.5. Here it is 1.5. Sorry, this is 1.5 minus 0.5 into xd. Now after that you will see that we can write this final equation as, we can write here as, what is the value here, this is what is that here, 5 into xd here. So we can write this. So finally you can write dxs by dt, that will be equal to here, if we divide it by 10, then we can write here it will be equal to 0.15 minus 0.5 xd. So this is your final equation. This is one differential equation from this material balance, that is unsteady state material balance. Now in this case, since we know that the xd will be equal to xs by 1 plus xs, so if we substitute here this xd value, finally then we can write this equation as xs dxs by 0.15, that minus 0.5 x s divided by 1 plus here xs, that will be equal to dt. So in this way we can have this equation in terms of xs and dt. Now this xs, that is steel concentration, will be changing with respect to time, and you have to integrate this equation within a certain limit of that as per condition given in the problem. So we can write here integration of, here concentration is changing from 0.30 to 0.40 of this dxs by 0.15 minus 0.5 xs by that 1 plus x5 xs. So xs that will be equal to 0 to here you can say t dt. Now after that, after getting integration within a limit at that t is equal to 0, initially steel concentration is 0.30, where you have to find out the time at t is equal to t, this x is to be 0.40. So based on this limit, we can have this integration of this 0.30 to 0.40 of dxs by 0.15 minus 0.5 xs by 1 plus xs, that will be equal to 0 to t here dt. So, from this we can have that t will be equal to 0. It will be as 5.85, this will be in hour. So, total 5.85 hour time will be required to vapor this mixer to get this composition of butane from its initial to the final of 0.40 there. So, in this way we can say that it is 5.85 hour will take to change the concentration of steel from 40% to 30% to the 40%. So, this equation unsteady state material balance, I think it will be helpful to do further this material balance in unsteady state condition. So, let us do another example for this. Let us consider a liquid tank of 1.0 meter square here. Cross sectional area is here 1.0 meter square, and it is filled with water at a rate of a meter cube per second. A is certain amount, let us consider a general a meter cube per second. Now, when the height of the liquid is h1 meter in the tank, a control valve installed on the exit stream at the bottom of the tank that opens up, and the liquid flows at a rate proportional to the head of the fluid as B into H meter cube per second, where H is the height of the liquid in meters. Now, in this case you have to express height of the liquid as a function of time. What is the steady state height of the liquid in the tank? A and B are constants here. So, basically you know that initially there will be certain amount of liquid. Now, if you allow some liquid here in this tank at a certain flow rate of a meter cube per second, and you will see to keep this initial volume inside the liquid constant, then you have to allow it to flow out from this outlet stream. So, there you have to maintain that output rate there, so that the liquid inside the tank will be constant. So, that will be your steady state, but here in this problem it is not there. You will see that initial volume will that gradually you will see that either increasing or decreasing as per that input and output flow rate there. If suppose input flow rate is lower than this output flow rate, you will see that the liquid whatever initially was there inside the tank, it will be decreasing, and accordingly height of that liquid will be decreasing with respect to time. If suppose inlet flow rate is higher than the output flow rate, you will see that liquid will liquid level will increase in the tank with respect to time, because that volume will increasing, because the inlet flow rate will be higher than the outlet flow rate. Now, in this case you have to if suppose A is higher than this outlet flow rate of B into H. So, in that case liquid flow rate will increase, and again if suppose here outlet flow rate is here, you will see that greater than that input flow rate, what will happen, that liquid level will decreasing at a certain flow rate. Now, in this case what is the steady state here, what should be the that height of the liquid as a function of time, that you have to calculate here, you have to find out or you have to express this. Now, this tank cross sectional area is given 1 meter square, whereas the inlet flow rate is given a meter cube per second. Now, how to solve this problem here? Now, how to express this height of this liquid that is changing with respect to time there. Now, what to do here? Again we have to do here material balance, which is unsteady state. Now, if we do that unsteady state material balance, unsteady state material balance, we have to consider in this case, in this problem, in this case we can say that generation will be equals to 0, consumption will be equal to 0. So, we can write d m by dt, that will be equal to in minus out, where m in as a rate minus m out, that means output flow rate of that mass. So, here this is accumulation and this is input rate, this is output rate. Now, according to this material balance, what we can write here, in this case first of all, what is m here? M is nothing but density into volume. So, it is basically rho into volume is what? Cross sectional area into height of the liquid. H is height, A is the cross sectional area. So, here A is basically pi into d square by 4, d is the diameter of the tank, and m dot, that is mass flow rate, here m dot will be equal to then rho into v dot. What does it mean? That is mass that is per unit time, what is accumulated inside the tank, that will be based on that volume rate that is increased or decreased inside the tank. So, that can be obtained just by rho into v dot, where we can write here rho is the density, where rho is equal to density and v is equal to volume, v dot is equal to volume flow rate, volumetric flow rate, and m dot is equal to mass flow rate, or you can say that mass accumulation rate. Now, simplifying this material balance, now simplifying material balance, we get d rho A into H divided by dt. We have just substitute the value of m here as a rho into AH, that will be equal to rho into v dot in minus rho into v dot out, which implies d H by dt, that will be equal to what? A minus B H. Why? Here see rho and rho, this is constant, that is here incompressible flow. So, rho will be constant and it can be omitted from this left hand side and right hand side just by dividing the both sides. And then here you will see that B in is given as A and outlet of B is given as BH, and in this case you can then write here this that dH by dt will be equal to this here. One important point here, it will be coming AH here. So, A will be remain here in this case. So, we are getting this equation here as per this. Now, per unit cross sectional area we can write A is equal to 1, since it is given as per problem A is equal to 1. So, we can write A will be equals to 1. Next what you have to do, you have to that integrate this differential equation of this dH by dt, that will be equal to A minus BH. Now, integrating this equation here in this case. Now, how to do this here, dH by, here you have to write A minus BH as integration here, that will be equal to integration of dt. Now, as per you can say that that initial condition as at time t is equal to 0, the height of the liquid inside the tank, it will be as H is equal to H1. It is given in this picture here. Initially up to this height was there, that is at H1. At any time that height will be H. Now, in this case we can then write here, we can write here H1 to H as dH by A minus BH, that will be equal to 0 to T as here dt. Now, after integration we can write, after integration within this limit we can write, after simplification H will be equal to A by B minus A by B minus H1 into e to the power minus B into T. So, this will be your solution of this integration. So, this that height at any time t, how is it related? So, H will be equal to A by B minus A by B minus H1 into e to the power minus B t. So, this will give you that with respect to time, that height will be changed. Now, that depends on this input and output that flow rate, and also that coefficient A and B here, or constant A and B here. That this A is that input flow rate and B is here the coefficient at this outlet flow rate. How that output flow rate depends on that height of that liquid inside the tank at any time t. So, that B there. So, initial height is H1. Now, the last portion of this problem there, suppose what is the steady state height of the liquid in the tank? A and B are constants here. Steady state condition, at a steady state condition, we can say, we can write here that d H by dt, that will be equal to 0. Therefore, we can write here the steady state height as Hs, that will be equal to, what will be the value here, because dH by dt what we got here, this is basically dH by dt, that will be equal to A minus BH, that means here A minus BH will be equal to 0 at a steady state condition. So, which implies H will be equal to simply that A by B. So, this is your at steady state condition what should be the height. That means here if suppose inlet and outlet flow rate will be same. So, in that case this steady state height will be equal to A by B here. So, if you consider that A is equal to suppose 1 meter cube per second and B is equal to suppose here coefficient is 2, then steady state height will be equal to 1 by 2 here. So, it will be simply half, that is Hs, half meter there. So, in this way you can calculate that steady state condition what will be the steady state height of the liquid inside the column. So, this is one example of this unsteady state material balance equation. Let us do another example here, dilution of salt solution. Now, the average here ocean water of salinity is 35 ppt that flows into a 100 liter of tank that containing 1.5 kg of salt, let us consider, at a rate of 5 liter per minute. Now, the salt solution overflows out of the tank at 5 liter per minute. Now, how much salt will remain in the tank at the end of 15 minutes, that you have to find out. Now, assume the fluid in the tank is well mixed and the density of the salt solution is constant and equal to that of water. Now, in this case you have to remember, if 1 kg of salt in 1000 gram of water, the salinity will be equal to 1 ppt. So, 1 ppt how it is related, that is given here. Now, basically this is ocean water, that salinity is 35 ppt, that is flows into a 100 liter of tank that contains 1.5 kg salt, and it flows at a rate of 5 liter per minute. Now, the salt solution also overflows out of the tank at a 5 liter per minute. Now, in this case you will see that the salt will be leaving from this tank. Now, how much salt will remain in the tank at the end of 15 minutes, that you have to find out. So, let us do this problem here again as per unsteady state material balance equation. Now, in this case we can write this general unsteady state material balance, general unsteady state material balance equation as here dm by dt, that will be equal to m dot in minus m dot out plus m dot generation minus m dot consumption. Since there are no reactions, so we can neglect this generation and also consumption terms. So, the final general material balance will come as dm by dt, that will be equal to m dot in minus m dot out. Now, if we replace this mass flow rate in terms of concentration, we can write here d into V C, V is the volume, C is the concentration, by dt, that will be equal to then in terms of flow rate inlet condition into C in, that is concentration of the inlet stream, minus again V dot out, flow rate at the outlet stream with a concentration of C out there. So, this you can write here in this way. Now, assuming the solution in the tank is well mixed, that as per problem, and the outlet salt concentration you know that equals the concentration in the tank. Assume here outlet, the outlet concentration equals the concentration in the tank, So, we can write here d V C by dt, that will be equal to V dot in into C in minus V dot out into C out, C out that is basically is C here, C out is basically as you know that C. So, here we can write again, if we consider that V, if V in, that is inlet flow rate, and outlet flow rate of this stream is equal, then we can write here, as we can write V dC by dt, that will be equal to, here we can write here what it is given, that okay, let it be here V here in dot C in minus V dot out, that is C, and in this case then we can omit all those things here. In this case then we can omit all those V terms here, and after that we can get that integration of C inlet and C outlet, and solving that equation we can get, solving the resultant differential equation, as per problem given. We can write C, then at t is equal to 0, it will be equal to 1.5 kg per 100 liter of solution. This is 0.015 kg per liter there, and C in that will be equal to 35 ppt, that will be coming as ultimately 0.035 kg per liter. So, this is your C in there. Then after integration, the concentration of the salt, okay, here we can say that the concentration of the salt, then as per integration, then the concentration of salt in the tank after 15 minutes, that is 90 second, is it 15 minute? No, that is what, 900 second, is approximately will be is equal to 0.035 here kg per liter, since the tank is 100 liter, and accordingly the amount of salt is 3.5 kg. So, this will give you that after 15 minutes this amount of salt will be there inside the tank. Okay. So, let us do another example, this type of problem to solve this, like example for sewage treatment there. Now, in a sewage treatment plant you will see that a large concentrate tank initially contains here 4,40,000 liter liquid and 10,000 kg fine suspended solids. Now, to flush this material out of the tank, you will see water is pumped into the vessel at a rate of 40,000 liter per hour, and liquid containing solids leave at same rate. Now, in this case estimate the concentration of suspended solid in the tank at the end of 4 hours. So, here the input and output flow rate of this tank is 40,000 liter per hour. Now, because of this stirring and aeration process, you will see that fine suspended solids, that it will be coming out from this outlet, and there you will see there change of concentration of that suspended solids inside the sewage treatment will be there with respect to time, that will change. Now, in this condition after 4 hours, what should be the that concentration of that suspended solids, that you have to find out. Now, again according to this problem, if we do the general material balance here, since there is no reaction here, we can also neglect here that generation and consumption terms, and then finally we can write that material balance equation here, material balance equation as here dm by dt, that will be equal to m dot in minus m dot out. Now, replacing mass flow rate in terms of concentration, we can write dVc by dt, that will be equal to V dot in C in minus V dot out to C out, or since here V dot in and V dot out is equal to 40,000 liter per hour, we can write the same amount here in this equation, or you just keep here and finally you can substitute that value. And in this case the outlet concentration of the suspended solid will be considering that the concentration will be in the tank itself at that particular time. So, we can write here dVc by dt, that will be is equal to V dot in C in minus V dot out, C out will be equal to simply C. We can consider here, that means this concentration is at a certain time t in the tank. Now, here this since water is flowing into the vessel at a rate of 40,000 liter per hour as input rate, and also if we consider that only water balance, accordingly we can write here this as d v, we can keep it as constant. So, we can write here v into d c by dt, and here inlet here concentration that of solids in the inlet pure water is 0. So, we can write here 0 minus V out, that is at a certain flow rate is given there, that is V dot out, that is 40,000 liter per hour, and in this case here we can say that this C will be C at that outlet condition. Now, what is that initial condition that time t in the tank, that solid concentration? We have to find out first to solve this resultant this this differential equation of this concentration change with respect to time. So, for this so here we need to have this initial condition which is the concentration, which is the concentration of solids in the sewage tank at time t is equal to 0, where you can write C at t is equal to 0, that will be equal to what? 10,000 kg of solid in 4,40,000 liter of water. So, it will be coming as 0.023 kg per liter. So, this amount of solid will be initially in the sewage tank. Now, do the analytical solution, of the differential equation, that obtained as dC by dt, that will be equal to minus here dC by dt, dC by dt will be equal to here minus V, that V out by V into C. So, from which we can write dC by C, that will be equal to minus V dot out by V into dt. So, from this after integration we can have this C at time t and initial condition, suppose C 0, that will be equal to minus V dot out by V into T. This will give you your after integration, or we can represent it as Ct will be equal to C0 into exponent of minus V dot out by V into T. So, this is your equation for concentration at time t, okay, as a function of time t. In this case you can find out the concentration T at any time t here, concentration Ct at any time t, provided C0 and V dot out and also initial volume inside the reactor known to you. Now, substitute the known quantities here, substituting the known quantities as per problem, we can get Ct will be equal to initial concentration is 0.023 that we found, this is kg per liter into exponent of here what is the V dot out, this is 40,000 liter per hour divided by, that is V is 440 here thousands, that is 4,40,000, this is liter, but here as per equation it is minus. So, finally after simplification it will come as 0.016, this is kg per liter. So, this is your concentration for the time 4 hour, here it will be equal to like this. So, it will be 0.016 kg per liter, this concentration will be there in the outlet condition at time t is equal to 4 hour. So, in this way we can calculate by the material balance what should be the outlet concentration of this solution at a time t. Let us do another example of unsteady state chemical reaction. There in this case a material dissolves in water as per following law, it is given, that is Rd is equal to Kd NUD into CSS minus CAS, where Rd is called rate of dissolution, Kd is equal to constant of dissolution, NUD is the undissolved quantity at time t, CSS is given as concentration in the standard solution, and CAS is the concentration in the actual solution at any time t. Now, the saturated solution of compound contains 40 gram per 100 gram of water in a test run starting with 20 kg of undissolved compound in 100 kg of pure compound. Is found that 5 kg is dissolved in 3 hours. Now, if the test continues, how many kilograms of compound will remain undissolved after 7 hours? Assume that the system is isothermal. So, here in this case you will see that there will be a dissolution of material in water, that will follow a certain laws, that is dissolution rate laws. So, that dissolution rate laws is given as per this equation. Now, in this case the saturated solution of compound always contains 40 gram per 100 gram of water. Now, in an experiment it is seen that for a test run starting with 20 kg of undissolved compound in 100 kg of pure compound, is found that 5 kg is dissolved in 3 hours in that solution, in that liquid water. If the test continues there for a certain time, now you will see that after 3 hours, that how many kilograms of compound will remain undissolved if you consume the time at 7 hours. So, assume that the system is isothermal. In this case, there will be no heat input output there, at a constant temperature it will be there. So, to find out that kilograms of compound will remain undissolved after 7 hours, that you have to calculate. Now, in this case what we have to do, that first of all you have to consider that undissolved quantity at time t. So, assume that the undissolved quantity at time t is equal to n. Therefore, as per problem we can write the material balance as dm by dt, that will be equal to m dot in minus m dot out plus m dot generation minus m dot consumption. In this case you will see that there will be a generation here with respect to time there. So, at a time t the undissolved quantity will be there, and it will be generated, and it will be n. So, we can write here this generation time or accumulation time of that molecule here dn by dt, that will be equal to, here there will be no input, there will be no output as per problem, but generation is there, that depends on that rate laws. That rate laws as per that constant is k, and here what is that rate laws equation, Rd is equal to Kd NUD into CSS minus CAS. Based on this equation we can write this, then K into N into here 40 by here 100 minus 20 minus N by 100. So, this is your generation, that is initial minus final, minus here consumption is 0. So, finally, you can write here dN by dt, that will be equal to Kn into 20 plus N by 100 after simplification, which will give you dN by here N into 20 plus N, that will be equal to K by 100 into dt. Now, we can simplify it as or rearrange it as dN by N minus dN by 20 plus N, that will be equal to K by 5 into dt. So, in this way we can rearrange it. After that we can write dN by dt here, that will be equal to Kn, that means here Kn into 20 plus N by 20 100 from this dN by N into 20 plus N, that means minus dN by this is I think no, we can write here dN by dt, that will be Kn into 20 plus N by 100, from which we can write here we can write dN by N, that is plus minus dN by 20 plus here N. Okay, we can write it finally as more simplified form that we have written earlier also, dN by N minus dN by 20 plus N that will be equal to k by 5 into dt. Now, this is your equation. Now, you have to integrate this equation with boundary conditions. What is that boundary condition? Boundary condition as per problem as t0, that is at time t, at t0 is equal to 0, n0 is equal to 20 at time t 0, and then t1 is equal to 3. We can say that n1 will be equal to 15 at time t2 is equal to 7 hours, then n 2 will be equal to at h1 here, what is that, t0 is equal to 0, n0 is equal to 20, and t1 at 3, that n1 will be equal to 15, at t2 is equal to 7, then n will n2 will be equal to what. So, if we do this integration within this limit of here 20 to 15 as per boundary condition. So, we can write dn by n minus integration 20 to 15 as dn by 20 plus n, that will be equal to k by 5 here 0 to 3 as dt, which will be given as here n2 will be equal to 10.7 as k is equal to minus 0.257. So, finally, we can get this at t 2 is equal to 7, n2 will be equal to 10.7. Why? Because from this here 0 to 3, in this case you can get k will be equal to minus 0.257. So, after substitution of this k value again here for this limit of this time here 3 to 7, and within a limit of this here 20 to 15, you can get this n2 will be equal to here something 10.7. Here in this case final concentration is n2 this. So, we can get this here at a 7 hour time, this final concentration of this undissolved solid will be there 10.7 kg of this amount of total N2. In this case the total amount of here material, we can say that here compound will remain undissolved after 7 hour will be equal to N2 will be equal to 10.7 kg. So, we have solved different problems with unsteady state material balance. I would suggest you to further go through the example problems given in the textbook in example problem and solved by that authors, then you will understand more there, and also you can solve the problems with this unsteady state material balance there that is given in exercise also in the textbook, and you practice it. I think you can do. In the next lecture we will try to discuss something more about that unsteady state process, but that will be energy balance equation. So, thank you for giving attention for this lecture.